Well, oh, Zoom just told me it's recording now, so maybe we start now. Good morning, everyone. Thanks for joining our session. I'm Christina McPike, the Director of Energy and Sustainability at Wind Companies, presenting this morning with Scott Mainpa with the architectural team. Our presentation is crisis management, how historic preservation is tackling affordable housing and climate change. So Wind Companies is a 50-year-old family-founded and operated real estate development company. We develop, own, and manage mixed-income multifamily housing across the country. We own about 15,000 units in the Mid-Atlantic and Northeast, and manage nationally in 23 states and DC, another 100,000 units. So large landlord, large owner. Sustainability at Wind Companies is not new. For over a decade, we've had an in-house team dedicated to our energy and sustainability initiatives. It's one of our founding principles and guiding principles as a company. That means that we plug into just about everything we do, between acquisition, rehabs, and renovations of existing properties to high performance, ground up new construction, and of course, historic preservation, which we'll talk about during our presentation. And we've been lucky for 50 years to be working really closely with our partner and the architectural team. And with that, I'll let Scott introduce himself.
Yeah, so I'm Scott Mainpa with the architectural team. We were founded in 1971, and we're really driven by the commitment to exceptional design and unyielding focus on achieving our clients' objectives. Our firm is about 95 people strong, very passionate, very dedicated to a number of different sectors. Our experience includes master planning, large urban mixed-use developments, commercial, multifamily residential, senior housing, assisted living, hospitality, recreational, as well as hundreds of historic renovation designs that have really established the firm's national reputation in the area of historic preservation, adaptive reuse. Some of the awards, recent awards that we've gotten for those, have over 200 design awards, but some of the recent ones were Cobbett Hill Apartments in Lynn, Sterling Lofts in Attleboro, and the Tyler, which we're going to get into in East Haven. I personally joined the firm in 2006, and I was fortunate enough to have Bob Verrier as my mentor. He made me realize my passion for historic preservation and adaptive reuse, and I've been lucky enough to work with Win on many of these projects. So with that, I'll hand it back over to Christina, and she can start discussing the Tyler.
Thanks, Scott. So, let's make sure my clicker still works. Got it. Great. So sustainability doesn't necessarily mean exclusively environmental sustainability. That's what I'm usually talking about. That's how what I'm thinking about every day. But sustainability also means social and economic sustainability. And historic preservation really has the opportunity to check all of the boxes. And we've worked really hard as a team over the last 20 plus years to continually raise the bar on how far we can push every project that we touch in terms of sustainability. Obviously, climate change is here and it's now, and we have to figure out what to do about buildings, which account for nearly a third of all greenhouse gas emissions in the country. And more than 2/3 of all the buildings that exist today will still exist in 2050. So as we're thinking about carbon neutrality and decarbonization by 2050, we have to innovate and get creative with our existing buildings and energy efficiency retrofits. But we have to do so with historic preservation requirements in mind. And I think we've come up with a really great approach and sort of integrated design process and over the years, and we're excited to present 2 specific case studies today to show what we've been able to do. But we're doing so while creating new housing, while solving for an affordable housing shortage, and while resurrecting historic structures, often in downtown urban centers, and therefore bringing folks back downtown introducing new jobs and providing new opportunities in often transit-oriented neighborhoods. There are all kinds of altruistic reasons why we are building sustainably and thinking about and caring about green buildings and high performance design. There are also other industry drivers between code and zoning and permitting, but also financing. So for years, Win has sort of combined the historic tax credit with the low-income housing tax credit in order to secure adequate resources to undertake these complex types of projects. When seeking competitive low-income housing tax credits, we're working with state housing finance authorities and responding to their qualified allocation plans, or QAPs. And year over year, these QAPs have become more and more aggressive or stringent, or maybe environmentally responsible, in pushing us developers and owners towards higher performing, better performing buildings. And over just the past 5 years, I'd say the QAPs have really matured in how they're thinking about high performance design. And you can compete with your peers, other developers, getting more points the sort of further you can go. And so what that means for historic preservation projects seeking 9% competitive LIHTC resources is that we have to figure out how to compete with new construction high performance design standards at the same time in order to, call it, secure the higher points in the qualified allocation plans. Not an easy task, but something that we are working together even with SHPO and NPS and our design and engineering teams to figure out. There are other drivers as well. Electrification is a word I frankly don't think I used before 2 or 3 years ago, and now I might say it a dozen times a week. So between natural gas moratoriums, given gas pipeline and supply issues, or moratoriums based on emission reduction goals at the local or state level, these buildings can't use gas anymore, or are limited in how much they can use for heating and domestic hot water. And so we're electrifying these systems. And when electrifying these systems using heat pumps, we have to be really, we have to insulate and air seal our exterior envelopes, which is all the more challenging in a historic structure where we care a lot about the exterior skin of the building. So despite the barriers and challenges and maybe my scary introduction, we've been able to do it and we're excited to present on the Tyler and to present a new project, Stone Mill in Lawrence. So the Tyler is built, it's 100% occupied with a wait list, which is amazing. This was an old high school in East Haven, Connecticut, 3 wings, originally in 1936 with additions in 1964 and 1972. Is sort of maybe a grainy aerial shot, but we converted the 1936 wing and the 1964 wing into 70 new mixed income apartments. We demolished the 1972 wing, and the city of East Haven retained ownership of the rear section of the building, which is used as a gym and a swimming pool for the community to this day, and through construction, which was fun to coordinate. So in response to Connecticut Housing Finance Authority's QAP, which was awarding maximum points for passive house design, we identified the European Passive House Institute's EnerPHit standard as a way to integrate passive house principles in an existing historic adaptive reuse project. The EnerPHit certification path is really remarkable. Obviously, there are a lot of historic buildings in Germany where this certification standard originates, and they allow for specific waivers, and historic preservation is a reason why they may allow for a waiver against a prescriptive sort of energy requirement. You still have to satisfy the performance requirements, so maximum heating and cooling demands, but the way you get there can be sort of customized based on the building and project needs. So we were able to select that certification path and apply for the 9% LIHTC to CHFA and receive funding, which was critical in combination with federal and state historic tax credits to getting this project done. Here's just a shot of the original 1936 steel windows, the 1964 curtain wall. These are historic conditions that we had to replicate with the historic adaptive reuse scope of work, and presented numerous challenges related to EnerPHit, right? How do you replace an aluminum or steel window with a high performance replica model? And this was a specific area where we had to seek a waiver from the EnerPHit certification plan. As a school, there wasn't a ton of interior historic characters that we were, or details that we were preserving. Some unique wall tiles, terracotta flooring, those were all left exposed. So this was exterior wall area that we were unable to insulate and needed to sort of accommodate for elsewhere in the building with more insulation or more high efficiency equipment. So overall, the impact of the EnerPHit commitment added about 6% to the total construction cost of $1.2 million. This was spent primarily on more and better insulation, as well as extensive air sealing throughout the building. The EnerPHit program, similar to the Passive House New Construction program, has a whole building blower door test requirement at the end in order to reduce or really eliminate air infiltration through the exterior envelope, keeping all of your conditioned and ventilated air sort of controlled and within the thermal envelope. In addition, one of the major changes was getting away from gas heating. So the project incorporated a variable refrigerant flow heat pump system for heating and cooling, along with a very high efficiency energy recovery ventilation system that was aerosealed in order to really dial into specific airflows to bedroom and all living spaces throughout the building. The project relied heavily on an integrated design process. So this wasn't just TAT being a great architect, which they are, but it required iterative design and a lot of collaboration with the mechanical, electrical, plumbing engineer, with the sustainability consultant, which in this case was Stephen Winters Associates, as well as the general contractor. And I should mention, as well as SHPO and NPS, right? They are key partners in making this project happen. And they were extremely communicative with us around our EnerPHit goals and program. We had to come up with some specific sort of unique details as well in order to deal with the thermal bridging at the exterior masonry wall. We actually had a custom made sort of insulated return panel made for the sills, heads, and jambs of the window openings that wouldn't interfere with sight lines of the window. It's a unique condition and a creative solution that TAT was able to come up with. And as expected, the building required a lot of insulation, and with limited sight lines and therefore limited sort of volume to play with, we needed to select a high R value insulation, meaning there's a lot of foam in this building, and something that we're hopefully going to be able to improve upon in the next one, but just a reality of being able to get the R values that we needed at the roof and wall assemblies without building a 6, 7, 8 inch thick wall. We were limited to a 4-inch furred out wall assembly on the exterior envelope. We had inspections almost every week, including testing windows for air infiltration, the blower door test at the end that I mentioned before, but also inspecting insulation depths and quality, and looking for any conditions like the middle picture here, which is a concrete beam and a huge thermal bridge that's interfering or interrupting our insulation, which we actually had wrap up the ceiling on every floor about 2 feet in order to help bridge that thermal gap. This beam was interfering with the ceiling height, which interfered with the window sight lines. And so sort of dealing with this in real time in the field with the contractor happened all the time in this project, and I think will be something we'll be able to be even smarter about in the end. So we're taking all the lessons learned from the Tyler, which is a great project, and going even further at the Stone Mill in Lawrence, which is a project that's in design development now. This is the oldest structure in Lawrence, Massachusetts, just shy of 150,000 square feet. We're converting the building into 86 new mixed income apartments at a range of AMIs, or area median incomes, including 17 market rate apartments. Unlike the Tyler, which had gas domestic hot water and gas preheat for the ERV system, Stone Mill won't use any natural gas at all. It will be all electric. One of the sort of the impetus here, one in a long list, is the Columbia gas explosions that occurred in 2018, and a commitment from the Merrimack Valley to try to get away from and eventually eliminate and phase out fossil fuels as a result of the Columbia gas explosion, but also in alignment with Massachusetts decarbonization roadmap. So with the new building, not a new building, but a historic adaptive reuse and the production of new units in Lawrence, we committed to making them all electric so that we're not adding new fuel loads to Lawrence. And I want to give some credit to Department of Energy Resources for the Merrimack Valley Relief Fund, which is an effort underway currently in the state to help support high efficiency design and initiatives like what we're doing at Stone Mill. I'm going to let Scott get into the specific design details at this stage with modeling support from R.W. Sullivan, who's the MEP engineer, as well as their modeling from New Ecology, who's our sustainability consultant. The project is projected to use about 35% less energy and produce 30% less greenhouse gas emissions than a brand new construction code compliant building in Massachusetts today, which I think is an enormous accomplishment that we're really proud of and excited to deliver on early next year. So with that, Scott, I'm going to hand it over to you to jump into some of the details.
Excellent. So yeah, as Christina was mentioning, Stone Mill, Lawrence, Mass, it's the oldest building in Lawrence. I think it's actually one of the only two buildings that remaining that are actually built from stone as well in that city. So as we were going through some of the highlights some of the design highlights that we'll be discussing is the all electric heating, cooling, ventilation, domestic hot water with the historic window replica windows and the simulated double hung windows. That was as Christina was saying before, collaborative process with our historical consultant, with SHPO and with National Park Service, as well as our engineers and our representative at Peerless Windows. It just goes to show that with these adaptive reuse projects, it really can't be designed by one person. You have to have a great team in order to get through them and complete the projects to everyone's liking. We're maximizing the insulation at the roof, the walls, and the slab. We'll kind of go into a couple ways that we're going to do that. Smart controls and thermostats, as well as the testing, inspections, and measurement verifications that Christina touched on at the Tyler. I think we're going to get even more stringent with some of those testing and inspections at Stone Mill. So going through the existing conditions, again, stone, exterior facade, the exterior walls vary in width, typical with masonry construction, turn of the century. The lower walls are thicker, and as you ascend through the building, the exterior walls actually, the depth of the wall gets thinner because there's less load that they're carrying. So it's more like a early on value engineering exercise where how they could reduce materials and get these buildings built. One of the key great features of this building are the windows. Everyone that kind of comes and looks at it and that's been on site, including engineers and everybody, kind of focus on just the stone and how the windows are orange and black. We've never really seen anything like that with the 12 basic 16/16 sash. So with historic preservation and with National Park Service and with SHPO, obviously the exterior of the building is a very high visible, high area of concern to kind of rehabilitate and bring it back to its original form and its original glory. So we work hand in hand with them, developing our approaches, and you know they review and eventually approve. So with the windows at this property, we have over 300 windows in here. One of the SHPO, one of the National Park Service requests was to do a full building survey on these windows. Basically, we had to survey every window, had to determine whether or not it was original or if it was replaced over time. And one loop, that this building threw at us is all the windows appeared to be original. But then, looking at some of the glazing, it wasn't consistent with glazing of that time period. It almost looked fabricated, newer glazing. So our historical consultant at PAL, she brought in a window expert, and he looked at every single window on this property and actually determined that 5 windows were original. They happen to be on the roof level on the stair towers. The rest of them, even though they look original, they were actually replicas that were stolen from the Everett Mill across the street and were used as replacement. So had most of these windows been found to be original, it would have required them to be reglazed and not necessarily replaced. And that would have definitely put a strain on our design, the 100% electrified design, just because we're not able to get that thermal performance out of that window and that air leakage performance. Another thing to note is when we're talking about insulating the exterior walls, this really only will work if your existing building has plaster on it. If you have exposed brick walls, it's probably not the right decision to go all electric, because SHPO and Park Service are going to want to not cover up that existing fabric and would like those masonry walls exposed. So, as you know, not very much thermal performance in an exposed masonry wall. The next slide. So some of the, this is just a building section and just kind of showing some of the design aspects that we're working with. So one of the key things is we're working with a pitched roof. Most of the mill buildings or school buildings that have come across, there's, it's a flat roof or 1 to 3 pitch that, we can still put mechanical equipment on. And given the sight lines, if you've ever been to Lawrence and if you've driven down to see this building, you'll notice once you get off of 495, you're basically coming down and this is right in front of you. So don't have the sight lines to put mechanical equipment on the roof. We have an existing slate roof that we are replacing, but we do have this attic space. And so we decided to go with a cold attic approach and essentially, replace the slate on the exterior, do the structural rehabilitation on the inside, but then to actually create our roof and create our insulation membrane inside that attic just above the units. So we're going to go in there with some 2x framing, lay that down. We're going to spray foam to get a nice air seal between the units and the cold attic. And then on top of that, we're going to drop our polyiso rigid roof insulation and protection board. So we're essentially going to be building a mechanically fastened membrane roof within the attic space to be able to use that attic as our mechanical room, but also provide the thermal performance and the thermal barrier that we need between the conditioned space and the cold attic. So overall, our attic's going to be an R50. Another on this slide, another issue that we're really running into time and time again is flood levels and flood elevations. Historically, these buildings were built on bodies of water, riverways, to be able to harness that hydroelectric power. Unfortunately, with climate change and flood level being rising, and FEMA updating all their firm maps, a lot of these buildings are ending up in floodplains. So in order to combat that, we do have to raise the slab down below. I believe we have to raise it approximately 3 feet to get it out of the floodplain. So we do some aspects, that if you raise a floor, it might get into the window. We were lucky enough that it's still below the window. It doesn't adversely affect any of that historically. What it also allows us to do is really bump up the insulation on that slab and put that slab at an R30. Also increase the thickness of the perimeter insulation to double or even triple times code. The other cool feature about this roof is there's a number of different skylights, and again, with working with SHPO and National Park Service, we've been able to come up with a plan to replace those skylights with louvers, and that allows us to be able to get exhaust fans that are going to be able to circulate that air within that cold attic space for our mechanical equipment, for all our VRF systems that are going to be going up there. So that's key with having that be an indoor space to be able to circulate that outside air within there. So you can see there's a number of existing skylight locations that were original to the building that are going to be reused and put in with louvers, as well as a couple of windows on the ends of the buildings that will also be retrofitted with a louver type assembly in either the upper or the lower sash to, again, circulate that air and allow us to hide all of our mechanical systems up within that cold attic space. And working with R.W. Sullivan on this project, it's really, I know Christina gave them a nod early on with the energy modeling and all that, but it's been a really great process going through and kind of coming up with these solutions. It's the first time, we've kind of had to, every mill building is different. So it's one of the first times going through this design that we've had to come up with a couple different solutions that aren't necessarily your standard practices in construction, but will work nonetheless.
It takes a creative MEP engineer to come up with the plan that we're showing up on the slide right now. And this is only half the building, so the other half of the pitched roof is just about as busy. I just wanted to elaborate quickly. We are heating and cooling the building with a VRF system similar to the Tyler, but capable of simultaneous heating and cooling, as opposed to a sort of a two-pipe traditional changeover system, which is going to be really important as this envelope is so robust. We expect the cooling load to be larger than the heating load at the end of the day, and we'll be monitoring for that. But we need to be a little bit more flexible and cooling during the shoulder seasons, and not only cooling in June, July, and August. It's fall today and in the 80s, so the system will allow for that. And while we have operable windows throughout, we are also mechanically ventilating the building with 2 energy recovery ventilators, similar to the Tyler, except with a heat pump for heating and cooling that make up air. And so the energy recovery ventilators are removing air from corridors as well as kitchen, bathrooms, and apartment bathrooms and kitchens, and essentially extracting the energy from that interior air and using it to precondition outside air, which we're delivering to all living spaces, bedrooms, living rooms, and corridors throughout the building. It's a really efficient way to provide balanced ventilation air to the building. And then for domestic hot water, again, all electric, there are very limited options in the marketplace for doing this today. It's important for us in the low-income community to pay for as many systems and utilities as we can, instead of putting those utility costs on the resident. So all of these systems are central, meaning the landlord or the owner is paying the majority of the load. So to identify a central electric domestic hot water plant that can serve 86 apartments is no small feat. We're working closely with Mitsubishi on their newer air-to-water heat pump system, which is not actually commercially available today, but they've been working with us with RW Sullivan to design and specify that system anyway, with the assumption that we'll be able to actually buy and install it next year. So just wanted to add a little bit more color into the MEP systems.
And the fresh air, the makeup air, since we are making this building tight, to have that run continuously and year round is really just a benefit to the end user, who's who's the resident, and also the shoulder seasons as well. As any property manager knows, that this time of year, when you have to do the seasonal turnover and drain the chiller and all that, you get residents complaining, and why isn't their AC doing cold air on a day like today? But having that control year round and being able to pump the fresh air into the building continuously just really makes for a great comfort level for the resident. So our exterior wall detail. So we've always gone back and forth with thermal bridging, metal studs. I mean, typically when we're firing out these walls, we'll be using metal studs. And as Christina was able to petition the DOER and get the project a large amount of grant money, we've been able to get creative and try to limit the amount of thermal bridging that we do, because we are going all electric, and really to kind of make that exterior wall perform as well as it can, while sticking with the Secretary of the Interior standards for the maximum of a 4-inch projection. So what we've come up with here is basically we're going to be framing all the exterior walls with wood studs on the flat, so that we just increase that amount of insulation that's behind them to limit that thermal bridging from the exterior wall. Because as I kind of mentioned before, the depths of the wall, the ground floor, it could be 29 inches thick, which sounds like a lot, but when it's masonry construction, that doesn't really give you a high R value. But then when you get up to the 4th floor and the attics, the wall is only 18 inches thick, so you're going to get even less of an R value with that wall up there. So being able to insulate that wall and get as much insulation thickness against that wall and before the stud to limit any thermal bridging is really just going to advance the design and make the building all that much better and energy efficient for the 100% electrification. Going into the windows, this was a great process where Christina introduced us to Peerless Windows. We've used them in the past. They got a great product. I personally had never used them before, but the representative there, Dennis Spear, he's been excellent. So Historic went out and did a detailed survey and evaluation. We typically use like just an extruded thermally broken aluminum frame on these windows that get a U value of 0.42. Higher the U value, the worse performing the window. With this window, we're going to be able to get that down to a 0.29. So huge reduction in the U value, which is just going to help our performance even more. A couple of key features of this window, just going with Historic. They're all historically double hung windows. Double hung windows or even single hung windows are very leaky as far as air leakage. So what we've come up with here is this is actually going to be an awning window. The full unit on is a top tilt out awning. It's going to resemble a double hung. It's going to be a simulated double hung, which we have that meeting rail detail there, showing the true glass being in different planes and the shadow line that's going to be able to be produced on the bottom sash. So again, by doing the awning and simulating the double hung, that just makes the window perform all that much better and allows us to be able to do the 100% electrification. We've had this gone through. Our part 2 has been conditionally approved. We're working through a couple of those conditions, but the windows were well received, and we're very excited to be able to gear up with Peerless and get these windows into the building. And we'll be proceeding with a mock-up. Basically, the mock-up, I think you saw some of the wainscoting on some of those interior photos. So that's also historic to the building. So not only are we going to be insulating the exterior walls, but we're also going to be replicating that wainscoting condition. And the picture rail that's at the top of that, the rail detail that was about midway up on the window in one of those photos. So it's really been a collaborative process, and again, you have to have a great team in order to do that, and to get through some of those conditions. We're going to be we've been asked to do mock-ups, and the mock-ups are going to be good for us as well, because it'll allow us to see what works, what doesn't work, what we were going to need to change when we get into the wholesale construction early next year. And just going in on some of the window design details. So on the left is what we proposed, basically not to fur out that the jamb as much as possible. The modelers came back and identified areas of weakness in that wall construction, specifically for mold, given that there's no insulation behind that hat channel. On the right is what they proposed, but obviously, that's not going to fly with historic preservation. It just doesn't mimic the existing condition of that window jamb in the window trim. Traditionally, the drywall and the plaster did not go up to the frame, to the window frame. So this is just an example of how we're going to go through this iterative process with the energy folks and the engineers, and how it's a back and forth until we can find a solution that works for everybody. So the potential improvement, although we get a lot of insulation in that jamb, it's not going to be conducive to maintaining or replicating the existing historic fabric in there. So we're going to have to go back and go through another round of this, and maybe find a different material, maybe an asymmetric channel that has one leg open, where the insulation can get behind it and not create a gap where there's a weakness for mold. This is, I was talking about the slab a little bit earlier. So we need to put in crushed stone. Obviously that height varies from 2 feet to 3 feet. And that's again to get it out of the floodplain, and also to get a little freeboard on that floodplain to account for the next 150 years that this building is going to be standing until its next rehab. So we're doing 6 inches of just continuous rigid insulation to give us our R30, and then we're doing 2 inches around the slab perimeter. That'll get us double what code recommends, which is R5.
Similar, we did a similar detail at the Tyler as well, driven specifically by the EnerPHit program, which has comfort criteria requirements. So the surface temperature in any living space can never drop below, I think it's 58 degrees. And so we modeled the slab for units that were sort of the garden level units or ground floor level units. And modeling showed that in the winter, the floor could actually get too cold. And so in that example, we also had risk for condensation and sort of durability concerns. So it wasn't in a floodplain in East Haven, Connecticut, but working with SHPO and our historic consultant, we were able to actually raise that slab by 6 inches in the ground floor of the 64 wing of the Tyler. Similarly, but for a different reason, we're doing the same at Stone Mill, but sort of checking 2 boxes at once, right? In terms of durability, comfort, thermal performance, but also to avoid any flooding risks. So we're learning to, when we ask questions during design development, try to think sort of holistically and not only try to solve for aesthetics or durability or mechanical loads or right, and trying to come up with solutions that can solve for multiple factors at once. And I think this is the last slide. We have our contact information here, which hopefully you can read. I always try to plug as many beautiful TAT design buildings in the background as I can. But I believe we have 10 minutes or just shy of that for questions. Before we jump into questions, I'll add, and I kind of glossed over this at the Tyler, just trying to be cognizant of time. After construction at Stone Mill, we will do a whole building blower door test, which means we, and in addition to that, we will test the apartments for compartmentalization. And so this is related to indoor air quality, controlling odor, but also sounds and air movement between apartments. So apartment to apartment and apartment to corridors, but also from the building to the outside. And so we want to keep thermal and conditioned air inside the thermal envelope, and we want to control air movement between apartments as well. And we generally follow the EPA Indoor Air Plus standard, which is required for Energy Stars, required for FIAS passive house certification in new construction. It's not technically required anytime we do a historic adaptive reuse project. We're actually exempt from energy code in many cases, but in all cases are trying to again, sort of outperform what we might otherwise have to do anyway. And the Tyler and Stone Mill are really good examples of where we're doing that. So in addition to compartmentalization testing, so testing air leakage at each individual apartment level, where we'll have a blower door in the apartment door, and we'll pressurize that apartment and measure air leakage or air infiltration to or out of the apartment. Sort of on a mega scale, working with New Ecology, we will do the same test on the entire Stone Mill building. And so they'll probably have multiple blower door fans set up at a few different doors within the exterior envelope of the building, pressurize the entire building, and we'll be able to actually measure how much air is being lost through our exterior envelope. So the sort of total sum of any and all leakage from the windows, through any venting, through any piping, any penetrations anywhere in the envelope, it's going to come up, and we'll be able to see it in the blower door test. And we'll do a blower door test, a sort of interim blower door test before we're finished with construction to make sure that we're either on the right track and or have a plan for sealing any penetrations in the air barrier in the building. And then again, at the end of construction, when all the MEPs are in and tested and balanced, and before residents move in, so that we can hopefully achieve a final whole building blower door test consistent with the passive house standard. We did a whole building blower door test at the Tyler. Because of COVID, our curtain walls at the 1964 wing were delayed about 6 months. And so we proceeded with completing the 1936 wing ahead of the 1964 wing. So if you're following, doing a whole building blower door test is really difficult when you suddenly decide to essentially treat it as two different buildings. So we actually did two partial whole building blower door tests at the wing levels, the 1936 wing and the 1964 wing, which are fully attached buildings. So we built sort of temporary walls to attempt to separate the two wings and test it that way. They tested really, really well, but not as well as we had hoped with the EnerPHit program target of 1 ACH50. So we're still actually working with Stephen Winter's associates and with EnerPHit on evaluating the final result of that test. We have a very tight envelope. The residents barely have to use their heat in the winter at the Tyler, which is, I think, a pretty remarkable achievement. But unfortunately, we were losing air basically from wing to wing, but not to the outside. So we're confident that we'll have a better outcome with Stone Mill in the end. Okay, so we have a few questions in the Q&A box, and I think we have 5 minutes to go through them. So I'm going to stop sharing my screen, which I think I did that correctly. And Sky, I don't know if you see the Q&A box, but
Yep,
I
got it
have it
open.
up on my screen here. So we'll just start from top to bottom. Since cities are increasingly moving away from natural gas, and many homes have gas boilers and radiant heat, do you have a suggestion for an electric product alternative, especially one that would be compatible with radiators so those don't all have to be replaced? It's a great question. Electrifying our homes and small multifamily and large multifamily alike in the state is going to be really, really challenging. Luckily, heat pump technology has advanced a lot in the last 10 years or so. What used to only be in the South and working in hot and humid climates now is available in cold climates. So I do think heat pumps are a good direction to go in. Those are air source heat pumps. They wouldn't be reusing your hydronic loop in your home or your radiators. There are newer products and initiatives being taken to get away from refrigerant heavy systems like an air source heat pump and going with a water-based or even CO2-based system. And I'm not a mechanical engineer, but if you send me an email, I'd be happy to introduce you to some manufacturers reps that we've been working with as we attempt to get away from sort of refrigerant heavy air source systems to water-based. They're just not readily available. I will say the only way to really do that is with a low temperature system. Radiators originally were for steam and for hot water. This is 180-degree water in January. The heat pumps are never going to be heating the water up to that high of a temperature output. And so we really need to think about the building shell in order to reduce the load first, in order to be able to temper the space with a lower output system. Some questions went away, but
Yeah, that was me. And I was just responding to one of the ones regarding the peerless windows, but it went under the answered, Kyle. But did you explore restoration of the historic wood windows, even though they were not original to the building, with weather stripping, storm windows, seek energy efficiency? We did, and it just with the single pane window, even with the interior storm windows, we weren't going to get the U value that was there. It's not so much we could have done with the weather stripping to make it, leaky, not leak, low expansion foam, all that kind of stuff. It's really just with the glass and with the muntins that were there that basically the glazing is put in between those muntins. So the muntins is just a great transfer, not a real good thermal break, and that cold is just going to transfer through there even with the storm window. So we did look into it. Unfortunately, with the 100% electrified system, was not going to be an option, just to make the building efficient. We don't want people to be paying. There's a couple of projects that I know of that went all electric that tried to do that, and people are paying their electric bills are like $400 a month in the wintertime. Easy.
Yeah, and as a affordable housing owner and manager, we have to be really cognizant of the energy burdens that low-income families face. A disproportionate amount of low-income household incomes are spent on utility bills. And so getting away from gas and heating with electricity is scary for a comfort reason, but also for your operating expense purposes and reason that we take really seriously. And it's still a concern. So again, we're really adamant that solving the building envelope first is absolutely necessary before we can comfortably electrify systems, unless of course we're able to get like a reduced rate for a high efficiency electric system, which is an initiative that we've seen sort of taking hold in other states, and I think would be a great idea for DPU to consider in Massachusetts. So there are concerns about heat pumps functioning in extreme cold temperatures. Again, that's the reason why the building envelope is so critical. We don't have a backup heating source, but we think that we'll be fine. The cold climate heat pumps are rated down to -13 degrees Fahrenheit. So I think we'll be in good shape. And I know we're at time. 35% lower emissions is not typical but hopefully setting a new bar for all of the historic preservation projects that we're doing. But it's so much lower due to the all-electric system and the installation levels. So thanks everyone for joining. Hopefully you cut our email addresses and feel free to follow up with any additional questions, and enjoy the rest of the conference.
Enjoy.